Yep. Then we'll start up again. What's this? Yeah. So I just read through the drill string and well the problem. So this is seen from the side. Again, drill string in the middle. The drill walls or well walls in green. Seen above is going to be like this. So now we defined a big R, which is the radius of the well walls or the well hole. And then you have this alpha IR, which is the fraction of the well hole, which is taken by the drill string in red here. This is kind of a scaling factor. Makes more sense to do it like this. Next, more assumptions. So we will assume something called the no slip condition. So no slip, which means that the velocity of the fluid along the walls is stationary. So this is a small u, yeah. So the velocity along here, the walls will just, well, stay put. Then we have the new I of alpha I r should be equal to the movement of the drill string itself. So we assume that the fluid is stationary at the boundaries here. Or, well, it's stationary here, and here it's firmly attached to the drill string itself. It doesn't slip. And again, for completeness sake, alpha I, we will define this to be from 0 to 1. So the drill string can't occupy the whole, the whole hole, or it can't be non-existent. So it should be more than 0 or less than 1. And it says how large portion of the hole is occupied by the drill string. So from this we can determine this C1 and C2 constants. So we get, well, 0 big U I R squared plus C1 ln big R plus C2 and QI equals big U I alpha I squared or big R squared plus C1 ln or the natural logarithm plus C2. So these two stem from the equation we had for small u. I think it was approximately here in the before the break. Anyway, we have these equations. So we have two unknowns, that is big C1 and big C2. And these can be determined as C1 QI dot plus big U I squared 1 minus alpha I squared and the natural logarithm of a I, alpha I, sorry. Then we have the other constant C2 minus big U I R squared minus C1 ln of R. Combining this, we get a new expression for small u, so that's ui, r minus big U I r squared 1 minus r over r big R squared plus C1 logarithm of small r over big R. And then this C1 is this expression. Yeah. So from this, we can observe that the velocity field, so this, is a function of the proportional radial position, small r over big R. And, well, this one is still unknown, since we haven't determined. So I'm going to write this up. So the velocity field is a func small r over r, and qi is still unknown. Since we don't know where is it. Okay. Since dz pi is not yet determined. Like so. So now we've kind of moved the problem to finding Ri. So we have an expression for Ri, but it's dependent on this Ui. So next up, let's try to find it. So before we find this, we will define even more, not constants, but even more variables, which is the flow Vi. So that's a big Vi. Vi. Oops. The flow Vi in the val should be known. And satisfied by a certain equation. By Pi minus pi alpha I R. So both of those are squared, Qi minus a big V without an index. And this one is flow of the mud pumped into the system. And then drill pipe. Like so. So this is one expression for it. And another expression for it is, well, can be found by integrating this UI over the annulus. So we are integrating it over, well, this yellow area. Then we get alpha I R to R, and then we would, of course, have this 2 pi R because it's an annulus. So we are first integrating here and then assuming it's like actually symmetric and stretching this across all of this, which is what you've done in calculus 2, I guess. Ui of R, the R. This thing is equal to plus 2 pi, again over the annulus, r, and then we have an expression for this. That is minus big U I squared minus r over big R squared plus C1 natural logarithm r over big R dr. Then we are going to introduce a small change of variables. To solve this better, so we are going to introduce a small v. This one is small, this one is big, I am sorry. Equals to small r over big R, which means that the dv is dr over big R. I'm gonna try to have my r's better. R, V, R. National Talk Like a Pirate Day. Up. So if you just hold this thought, we'll get an expression for v soon. So now we are going to solve this, but first we will introduce our new change of variables, which means we will get it on the form big V I 2 pi big R squared minus big U I alpha I to 1 V minus V cubed dV plus C1 integral from alpha I to 1 V ln V dV. Solving this these two integrals analytically should be a piece of cake. So then we get our expression for big V I as 2 pi R squared minus big U I all squared minus 1 over 4 1 minus alpha I power of 4 plus a half 1 minus alpha I squared. So that's the first integral plus C1 minus 1/4 1 minus alpha I squared minus a half alpha I squared logarithm of a I. Yes. And then you can also insert the expression for C1 to get an even less nice expression. Yep. So yeah, this C1 into there. So now we have two different expressions for this vi. We have this beast. I'm going to circle it. This beast and this slightly nicer thing here. What we can do then, well, they are two expressions of the same thing, so they must be equal. So we can set them equal to each other, which means that we get some expressions and more variables. So now we have an expression for big I as q dot over r phi I big V over p on pi r to the power 4 psi I. And then we've solved it. No. Phi I is the expression c minus 1 over 1 plus alpha I squared logarithm of I plus 1 minus alpha I squared, and psi I equals 2 over 1 minus alpha I power 4 plus 1 minus alpha I power of 2 to the power of 2 divided by the logarithm of alpha I. Yes, I think we have everything then. And it's worth to note that phi I and psi I are both positive when alpha I is contained between 0 and 1. So now we have an expression for big U, and we have everything here. Well, we can measure this. We know this. This is the radius. This is how much we inject, and this is the alpha I is the portion of our drill string, how much the drill string occupies the well. So coming back to this thing I just removed from the blackboard. We have small ui of r is q I minus phi I 1 minus small r over big R. Can you see this? R plus 1 plus phi I 1 minus alpha I, this thing squared, over the logarithm alpha I, R over R. It's the first part, minus psi I V pi r power of 2 1 minus r over big R. Is it to, we can read it? I squared logarithm of I, more logarithms, R over R. And then we can differentiate this and get C d u I over dr as qi dot 1 plus phi I 1 minus alpha I squared R, and then alpha I plus 2 phi I over R, big R squared, oops, R, plus Ci V over P R power of 2, also known as squared, 1 minus alpha I, this thing squared, R n Ri plus 2R over big R, capital R. That's one expression. Next, back to these friction forces, Ri. So, the friction forces acting on a small segment of this drill pipe or string on a segment string with length h, so part of the string, and then the friction or the viscous friction forces when it is moving up and down. How much is this? Well, Ri 2 pi alpha I of R, so this is the outer shell of the drill string. The length of it, h, viscosity mu, dr I at alpha I R plus Ri dp of the big V here. So, yes, again, we have two variables that look similar. We have R with a index I. This is the friction force. This without, or this R without a index is the radius of the hole. The length of the drill string, well, length h here, viscosity, and the radial derivative of this flow ui at the position alpha I r. So this is at the drill string. So this inner bit. This bit here, this is phi r, this point along here. And then we have this mysterious thing here. This is the friction force acting on segment I from the inside of the drill pipe. No, this is moved. So you have a friction force here, so because of the injected volume. Except, so this one is 0, except when I equals n, so then you're at the end of your drill pipe and you're not injecting anything there. So no extra. Yeah, this is given. This V is given. And this one is just a function of V. We won't go into the details around that one though. Yep. So hence we have a monstrous expression for this. So we have everything here now. We have this drui. This is this bit, and I'm just thinking, should I? No. Yeah. So now I'm going to write up the full Ri, the friction force. So I'm going to need some space. So Ri equals minus 2 pi, length of it, mu, h mu, 1 plus alpha I squared, 1 minus alpha I. So we'll shortly shorten this expression because we can't keep this up for much longer. The inverse of this, q dot I plus 4 h mu v over r squared, 1 plus 2 alpha I ln of alpha I divided by 1 plus alpha I, well, this thing squared, over 1 plus alpha I squared times the logarithm phi I plus 1 minus alpha I squared plus this constant thing here, the drill pressure, yeah, of V, like so. So in order for this to become more manageable, we will say that this thing is zeta I. I think I call this small c I in the note, but I will call it zeta I, just to, well, because we have a lot of different c's. And then this bit here is Vi of the applied flow. So then we end up with Ri minus zeta I Qi dot plus small vi of big V. So a lot more manageable down here. And also as an observation, we can see that this zeta I is always positive due to this expression here. So yeah. Then we can go back to the formulas we had in the beginning for all of the blocks, the force of the blocks. Yeah. So the matrix form of this. So I'm gonna write these again. MIQ double dot plus M1. What is this one? This is one. G B. Oops. B1 minus K1 Q1 minus Q2. No, big Q. Plus K2 Q2 minus Q1. And now we have an expression for this Ri, which is zeta I Qi dot plus this small vi. Sum should be 0. So this is for the first block, and for the ith block, except the first and the last, mi Qi double dot plus mi g b I plus ki qi minus qi minus 1 minus 1 plus ki plus 1 ki no q I plus 1 minus qi minus zeta I qi dot plus vi 0 minus, almost there, qn double dot ng n minus, yes, this should be a minus here. I forgot I had a plus instead of a minus there. So this is a minus. Let's see. Minus qn minus qn minus 1 minus, yeah, zeta n qn dot plus vn equals 0. So then we have this in a nice fashion. We can write this as big M Q, M Q vector double dot plus big C Q dot plus KQ minus G, well, this is a vector, minus V vector equals the, so right now I'm just introducing the driving force, F of t. Well, how does these look like? Well, M is a diagonal matrix, so I'm going to just write it as it. So M is diag minus M1 minus M2 minus Mn, and this is a nxn matrix. Your big C is also diagonal with these zeta ones, minus zeta 2, zeta n, still a nx n matrix. And then K as a tridiagonal matrix. So big K, K1 plus K2 minus K2 there, minus K2, K2 plus K3 minus K3, 0, 0 minus K3, K3 plus K4 minus K4, 0 here, 0 there, 0, and we end up minus Kn minus 1, K minus 1 plus Kn minus Kn, and in the corner, minus Kn, Kn, 0, 0, all of these are 0. Again, a n matrix. So then we have this one, and this one. Now we need G and V. I'm gonna remove this big. Well, V as a vector is just going to be all of these. So V1, V2, Vn, which is a n by 1, so it's a column. Then we have this G, which is M1, G, B1, M2, G, B2 und so weiter. mn g b n, also a column n x1, then this driving force is just going to be one element, but still a column vector. So this big Q, 0, 0, 0. So this first element here is the driving force. Yeah. And then this can be solved. It can be solved. But we are going to try to get rid of these. So we can apply some transformations and get a much nicer system. So now we're going to move more into the territory of math. I mean, it still has some physical meaning. We're basically reorganizing the coordinate system in a nice manner, such that it's easier to solve this. And yeah, Q. This is that's a vector for all of the Q's. So for convenience, we want to eliminate these two now. The G and V. These. So, coordinate transformation. We will introduce a y vector. So, this Q, y plus the inverse of k, minus 1, g plus v. Yep. But then we have a different problem. We have to figure out the inverse of k. I won't go into too much details, but this one can be written as, let's see if you get the system. So this is k1 at k1 at k1 at k1 at, let's see, yeah, it's supposed to be a hat here. That's the first column. Next one, k1 hat, what do you think the next one is? k2 hat. k2 hat, and then you have k2 hat, all the way down here, k2 hat, then you have k1 hat again, k2 hat, k3 hat, all the way down here, k3 hat, and then we continue like this, k1 hat, here, kn minus 1 at kn hat. And then yes, kn minus 1 at kn minus 1 hat. So do you see the system? So you have first just 1, 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, and then you have 1, 2, 3, 3, 3, 3, 3, 1, 2, 3, 4, 4, 4, 4, 4, and so on. And then the last one you have 1, 2, 3, all the way down to n. This one can be written in a nice fashion, and then we are soon finished. That's a good place to end. So all ki hat is the sum from j equals 1, I the jth element of inverse. And this is just elements. So right here we're lucky. We can have a nice inverse of our matrix. And using this transform, we end up with y plus c y plus k y equals f. Yeah. And a nice observation here is that when the driving force is 0, when the system is just there, and all the derivatives also 0, then your system is just still. So when you don't do anything with your system, the system doesn't do anything. So that hopefully makes sense, which means that it doesn't act on itself like ghost vibration or something. Yeah, but we still have some problems. So these are dependent on each other, but that's for next week. Then we'll start massaging this expression a bit more. More math. Yeah. So again, Friday we will have a guest lecture from Statoil, Ørjan Pedersen. I forgot the title of his talk, but it's on Slack and the schedule. Hope you'll be there.